Okay, hi everyone. So today I'm going to talk a bit about using hybrid fuzzy systems in AI-based robotics. To give you a little introduction about fuzzy logic, it is a way of representing knowledge when some concepts cannot be defined, like when they are uncertain, or if we give words like cool, warm, hot, they are very ambiguous. We don't know the exact, like we can't give a value to them. So in those kind of contexts, we can use fuzzy logic. So to give you another example, like I'm from Kandy and I'm going to university in Morotto. Like if I have a friend in Kadavatha, and so I would say that my friend in Kadavatha is not that far from the university. But if I go to my university and then ask my friend, where are you? Then in that context, I would say, you are still far away. So like that, based on the context, the definition of the term that we use can change. Like if I take another example, say we are at a restaurant and I want to decide how much I should tip the person who helped us. Like in that kind of a context, like if I'm using fuzzy logic, this is how fuzzy logic works. So if I'm going to use fuzzy logic to decide on what kind of tip I should give, I can. The first thing that I have to do is I have to identify what kind of like inputs that I should give for my system. Here I have taken the service and the food. So I can give these as the input variables. I can rate how much how good the service was out of 10. So if I say like I can say 3, and for the food I can give 8. So after defining those after like deciding on the input variables, and this is my output variable, and after deciding on that, the next thing is I have to come up with rules. Now these are just very basic rules. One rule is, if the service is poor or food is rancid, then the conclusion is the tip should be cheap. Like that I can define the rules. So here, when I give the service as 3, then I can map this value 3 with these rules. Sorry. Now, after coming up with the input variables, then I have to first define what are the linguistic terms that I'm going to use for that variable. So to define this service, I'm using like whether the service is poor, whether it's good, or whether it's excellent. So for each of those linguistic terms, I'm going to give a membership function. So this uh, first one is for poor, and for good, I have this membership function, and this is for excellent. And if I put all everything together, that's the membership function of service. And for food also, I have defined membership functions. And for the output variable also, we have these membership functions, and then I define the rules. And after that, when I get an input like service, I can map it with each of these linguistic term membership functions. So if I take the first rule, I'm going to map these 3 to this membership function poor, and I might get a membership value like 0.3. Like from 0 to 1, like it's the probability, right? So it is from 0 to 1, so the membership would be around 0.3. And when it comes to food, if I say it is 8, here it is like almost 0 if I take the membership function of rancid. And then I'm going to do the same for other rules as well. And over here, after getting those values, we are going to use an inference technique. I will talk about 2 inference techniques later. So if we are combining these 2 input variables using O, we can take the maximum. And if we have n over here, we can take the minimum. So like that, we can get the here it is O, so I'm getting this maximum value, and I'm going to clip out this output variable membership functions. So here, since I'm saying then tip is cheap, I'm going to take the membership function of cheap, and then I'm going to clip it out from there. And here in the second rule, it is saying tip is average, so I'm going to clip it out from the probability value that I got from this good membership function. Like that, after clipping out those membership variables, membership functions, I am going to aggregate them to get this final, uh, you guys can see, right? Get this final graph. And after getting that, I can use defuzzification methods. For example, here this is the centroid method, and there are other methods like highest maxima and lowest maxima, like that. There are different methods. So using that, I can change my fuzzy value into a crisp value. Like here it's 13.7. I can't. Yeah, 16.7. Like that, I can decide on the tip value. But if I used a machine learning model or a deep learning model, I would have to use lots of data for it. I would have to train it. So these are the two main inferencing methods that we usually use. Inferencing method means like when we are combining these rules together, there are different ways that we can get into map that into the output. Those are the inferencing method. So Mamdani is what I discussed over here. And in 𝘚𝘺𝘍𝘐𝘺 method, the important thing is here we can incorporate a weight value for the rule. So after getting that, rather than taking something like a centroid method, here we are taking the weighted average. So here how it works is similar to Mamdani method. We are taking those probability values, and then as the output, we don't have an output variable function. We don't have a membership function. We don't have something like that. We just have this formula. So we are going to take these xy values, and yeah, we are going to put in these xy values to get z, and the weight in 𝘚𝘺𝘍𝘐𝘺 method, the weight is either if we take O, we are taking the smallest probability. Sorry, if we are taking O, we take the maximum probability. If we are taking N, we take the smallest probability, and that's going to be our weight. So this way we can give more priority to rules that have more significance for our context. So in fuzzy logic, so when we use fuzzy logic, it lets us deal with partial truths, and by using membership sets and membership fuzzy sets and membership functions and rules to make our decisions. So what I mean by that is when we take conventional logic or like the probability theory that we usually use, we can those things work with absolute values like 0 and 1. If we take a set, a number could either belong to the set or not. So if you look at this picture over here, like we can't say a number we can't have partial truths, right? We should either put it inside or keep it outside. But when we use fuzzy logic, it operates with degrees of truth, meaning it can have partial truths. Rather than saying something is hot, either hot or cold, I can have in between values and say it is warm. So in robotics also, this can help us deal with real world uncertainty. Like when we are controlling a speed of a robot, like if there's an obstacle in front of it, we can make the robot gradually reduce its speed rather than stopping all of a sudden. So why am I saying we need to use fuzzy logic in robotics? So fuzzy logic can help us make smooth decisions, and fuzzy logic can reason like humans. Humans reason with rules, and this requires less computational power than when we are using deep learning models. Like deep learning models require a lot of data. And you also know that robots are usually in dynamic environments. So when we use fuzzy logic, we can make the robots adjust smoothly to the environment, and rather than like I said earlier, rather than making sudden moves, we can make it gradually adjust. And like if I say an example, when a robot arm is grabbing something, based on whether that item is like a delicate object. We can use fuzzy logic to make it like decide on how hard, like the force that it should use on that object. And so, what kind of methods do we usually use on robots to make decisions? So, we mainly use machine learning, deep learning, and reinforcement learning. So, the robots usually use machine learning to identify patterns in data, and then it use deep learning to do vision-based recognition, voice recognition, like that, using very complex data like images and voice. And it uses reinforcement learning to learn through trial and error. So let's talk about the challenges in this. So one huge drawback is the nature of like the black box nature in these techniques. We don't always understand how these work, like how it finally gets to that certain decision. So also in deep learning and reinforcement learning, it requires a huge amount of training data, and it makes it quite impractical and difficult to train them. So for example, like uh, if we train a self-driving car using reinforcement learning, obviously we have to do like millions of trials to train it. And if you are making a humanoid robot, like no matter how much we train it, like in the end there could be like a new movement where the humanoid robot can't understand what to do. So why do we need hybrid approaches? So if we use just fuzzy logic, it would be a bit too complex to deal with like a robotic behavior. The fuzzy logic can't do it alone. So, and on the other hand, if we use just AI technologies, it requires a lot of resources, and it would be kind of a waste of resources. So obviously the solution is to have both. And when we like when we are having hybrid method, the AI methods like machine learning, deep learning, reinforcement learning, those can help us learn optimal fuzzy rules, while the fuzzy logic can make the AI decisions more interpretable and adaptable to the situations or the context. Um, Okay, so now we know how why we need these hybrid approaches in AI-based robots. So there are three main types that we can use. Like we have neuro-fuzzy systems, fuzzy reinforcement learning, fuzzy deep learning, and some other methods. And each of these address like different challenges in robotics that we face, like adaptability, explainability, and efficiency. And talking about neurofuzzy systems, it is in neurofuzzy systems we use neural networks to like we use neural networks to for its adaptability, and we use fuzzy logic for its explainability. And I will talk about this at the end a bit more. And in fuzzy reinforcement learning, reinforcement learning is a very powerful but very powerful technique that we can use to train robots. But you also know that it requires a lot of training, and it lacks the explainability. In the end, we don't know how it learns. So by integrating fuzzy logic, we can guide the learning process and make it a bit more efficient. Like if we say there's a robotic like a robot path learning system, so in there we can use fuzzy rules to help robots navigate obstacles safely, and then we can use the reinforcement learning to decide on the best route after training. And in fuzzy deep learning, deep learning is really good with recognizing patterns and patterns um, like in images and um, audio clips. And fuzzy logic can help us interpret the patterns in the human readable decisions. For example, like if we have a robot arm, we can use deep learning to help the robot like identify the object, what kind of object it is, and we can use fuzzy logic, like I explained earlier. Like we can use fuzzy logic to like decide how much pressure it should use when grabbing that item. Okay, so this is the neurofuzzy system. I will explain a bit more about this one. So in the neurofuzzy system, we have two main components. We have the fuzzy inference system, and then we have the neural network. We use the fuzzy inference system to map the input to the output, and then we use the neural network to optimize its parameters. For example, like the neural network can learn from data and adjust the fuzzy system. Mainly, it can fine tune the like the membership function. That means if we have we can have membership functions like this. Some can have membership functions like this. There are different functions, so it can adjust those functions, and it can also adjust the strength of rules. Like earlier I explained, there's a weight value, so it can help adjust that one. And also it can adjust these boundary values over here, like whether hot starts from here, or like whether it's here or here. Like that we can adjust those values as well. So in the neuropathy system, we mainly have these five steps. Sorry, the five layers. In the input layer, like I'll take an example that's easier. So if we take that same tipping example, we can say this input is the service and this is the food. So here these represent the variables, input variables. So yeah, these are the linguistic terms of the input variables. So this might be good, this might be medium, this might be bad, like that. So we give this crisp value that we are getting service equals 3, like that. We are giving that value to get the membership value for these linguistic terms. Membership value means the probability of this value being belongs to this one. That's what membership means. So after getting that, we can map them to these rules. Like we can say this one might be service is good and food is good. This rule might be something like that. After like this is the rule layer. So after mapping it there, we can also calculate the weight value, and we can get the output of this rule layer. For example, earlier after taking the O, we took like when we have two input variables like this, then we map the value and take this probability outside, like that. Like that, we are taking that value out, and after taking that value, we are mapping them to the final output variable. So if this can be service is good, food is good, and then tip is high, like that. Like that, we can map them. And after mapping them, then we put these rules together into this declassification layer. And in that layer, we are getting the output. Now, I didn't mention where we are using when we are using the neural networks. So here in the input layer, we can use neural networks to, like I said earlier, also we can adjust these membership functions. Like we can decide what kind of a membership function will increase accuracy of our system. And we can also use this to decide on these bound values. And in here also we can decide what kind of rules will increase the accuracy of our system. Yeah, and also when we are deciding this weight, we can for that also, rather than taking the highest probability value as our highest or the lowest probability value as our weight, for that also we can create a function using neural networks. And in these two layers also, in the uh, in the output layer. Yes, in this layer, the inference layer, here we can define how rules interact with each other. So here, this is one rule and another rule. These are coming together. We can decide how they are going to interact with each other rather than like getting them straight away. We can, for this also, we can define a formula using neural networks. And then in the defalsification layer also, we can optimize this defalsification process, like rather than taking something like a centroid value, we can use neural networks to finally decide on the crisp value. Now, to do these things in neural networks, we can use different techniques like backpropagation, gradient descent, and we can train data. So, in using backpropagation, we can adjust the membership functions that we are using and the strength that we are giving to rules. And using gradient descent, we can we can decide the best rule weights that we can give to improve our decision accuracy. And by training data, we can by training data also we can improve the accuracy of our system. So that's about it. So later when you are building your own robots, you might be able to use fuzzy logic to make it easier, that make the training easier by defining fuzzy rules.